Hello, Organic Chemistry 2341. We're going to continue with the homework lessons for chapter 4. And there's my pencil. All right. So we're going to start out with 423, A, B, and C. Write a line bond formula for the following compounds. Okay. So just like we, when we do our nomenclature, we actually start with the biggest thing first. We're going to start drawing with the biggest thing first. So what we're going to see is we're going to see that this is pentane. So we're going to do 1, 2, 3, 4, 5. So that's a total of 5 carbons. And then we have dichloro. So we're going to put 2 chlorines on here, and we're going to put them in 2 different positions. We're going to put them in the 1 position. We can just start on this side or the other side. It doesn't matter. Chlorine. And then 1, 2, 3, 4. So the other chlorine has to go here. All right. So we started with the big thing, drew it out, and then added our 2 things in their correct position. Okay, so let's see, we're going to do B now, sec-butyl bromide. So let's draw our sec-butyl here. That's our butyl, and our sec-butyl group is going to be that group there. So we know we can start with that structure there. And then the only other thing on there is bromide. So we're going to put a bromine on here. And so that's we know it's going to go on this place, bromine. So we drew our substituent first because we knew how to draw that, and then we added our thing we don't have. Ooh, 4-isopropyl heptane. Well, we don't want to start with just the isopropyl. So what we're going to do is we're going to start with the heptane first. So let's see, we've got heptane, which is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So we have heptane. Okay, and then we want to find 4. So we're going to start from this side, 1, 2, 3, 4, and we're going to put an isopropyl group on there. So it's isopropyl. Okay, so see where we start with the big chain, and then we start positioning things on there. I'm going to just do the rest of them anyway for fun. Trimethylpentane. So let's go with pentane first. 1, 2, 3, 4, 5, and then we have a 2-methyl. A 2-methyl and a 3-methyl, trimethylpentane. Start with the big chain, go to the next one. So let's do another one, ethyl methyl hexane. So we're going to start with the hexane, 1, 2, 3, 4, 5, 6. Then we have a 2-methyl, starting to start on this side this time, 1. I'm going to start on that side. So we're going to do 1, 2. So we have a methyl there. 3 ethyl, so there's an ethyl on that 3rd one. Okay, all right, here we're going so well, let's just do the last one too. We have dichlorocyclopentane. All right, so we're going to start with the cyclopentane first, 1, 2, 3, 4, 5, and then we're going to do 1, 1, Cl, Cl, dichloropentane. Okay, so that is all of those. All right, so let's do 24. Give IUPAC names for each of the following. Okay, we're going to follow our rules and we're going to get this done. All right, so the first thing we need to do is find the longest chain. And if we're starting with A here, might be, no, not that one. And it could be either one of these methyl groups here. So it could be either one of those methyl groups. So what I'm going to do is I'm going to say, I'm going to try to get the longest, straightest looking thing here. So I'm going to say 1, 2, I'm going to say this is my longest chain. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Yeah. So when you count them all, that is our longest chain. So that's our longest chain of 10. Okay. So which side are we going to number from? Well, if we look on this end of the chain, we have a substituent right here. If we look on this end of the chain, we don't have a substituent until 1, 2, 3, 4. Okay, so let's number from this side. We have 4, 5, 6, 7, 8, 9. 4, 8, 4, 7, 8, 9. But if we number from the other side, we're going to have 2, 3, 4, 5. So we're going to number from that side. We're going to have to number from the left side because that's going to give us the lowest number set. Okay, so we're going to start numbering from here. So it's 1, 2, 3, 4, 5, 6, 7, and We don't have to number anymore because we already have all the carbons. 1, 2, 3, no, yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So we have our longest chain, we have our numbers down, and we now have our substituents. We have a methyl group, an ethyl group, and an isopropyl group. So if we have methyl, methyl, so we can do dimethyl. We have an isopropyl, isopropyl, propyl. We have an ethyl group, ethyl. And so alphabetically, ethyl is going to come first. And then we'll have isopropyl, and then we'll have the dimethyl for the methyl, not the di, just the methyl. So let's string that all together. Now that we know all of our different parts. And so our final thing is going to be, let's see, our ethyl group is on the number 5 carbon. So we're going to have 5 dash ethyl dash 7 dash isopropyl dash 2, 3 dimethyl. We have 10 carbons, decane. All right, so we followed all our rules. We found our longest chain, got our numbering system, assigned alphabetical order to our substituents, and put everything together. All right, so let's do B now. Right there. No. Okay, so let's do B now. Let's see, where's our longest chain? Let's see. Ooh, this is tricky because you want to say it's this one right here, but this only has 1 carbon and this has 2. So I think we have to have that little group sticking down the bottom as our main chain. So let's see, count just to be sure. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if we do 1, 2, 3, 4, 5, 6, 7, 8, our longest chain is octane. So we need to do that. So write down octane. Now we need to find our lowest numbering right here. If we start from this end, we're going to have 1, 2, 3, 4, 5, 6, 7, 8. If we start from the other side, we're going to do 1, 2, 3, 4, 5, 6, 7, 8. So let's see, in this case here, in the red numbers, we're going to have our substituents on 3, 4, and 6. On the blue numbers, we're going to have our substituents at 3, 5, and 6. So we have 3, 4, 6 or 3, 5, 6. So let's see, 3, 4, 6 is the lowest number set. So we need to use the red numbers for our numbering. So we're going to number from this side right here. And so that's going to give our substituent on the 3, the methyl. The 4 is the bromine, and the 6 is the chlorine. So let's put that all together. We have 4 bromo. We have 6 chloro. We have 3 methyl. And we have octane. Okay, so putting it all together, we have, let's see, bromo comes before chloro, so we have 4 bromo, 6 chloro, 3 methyl, octane. Okay, there we go. Let's do C. Okay, I'm going to go ahead and clear this out of our way so we can do C. All right, we have a bicyclo compound. Okay, so we have to use some rules for the bicyclo compound. First thing we want to do is count all the carbons in the entire thing. So let's do that first. 1, oops. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's a total of 9 carbons. So we're bicyclononane. So let's write that down. Bicyclononane. That's an O here. That's an O. Okay, bicyclononane. Okay, so let's start by getting our numbers that are going to be in that bracket. So we have an identification here. So what we're going to do is we're going to start at a bridgehead, and we're going to count the number of carbons in a bridge. So we're going to do, this first bridge is going to be 1, 2, 3 carbons. So that means there's going to be a 3 in our brackets. Starting in the bridge, we have 1, 2, 3. I'm sorry. And you count over to the other bridgehead, but don't count the bridgehead. We're only counting the carbons in the bridge. So when we go over to this side, we go 1, 2, 3. So we have another 3. So it's 3.3. And our last bridge is 1. So it's 1. So this is our bracket for the bicyclononane, 3.3.1 bracket, bicyclononane. And now let's do our numbering. Now, when we start our numbering, we have to start numbering from a bridgehead carbon. And so that's always number 1 is a bridgehead carbon. And then we're going to go around the largest one first. So these both have 3. So that means we can choose either one. So if we can choose either one, we're going to try to choose the one that makes our substituent on our smallest number. So by starting at this carbon here and going as 1, this is our 2 position. That puts our bromine on the number 2. So that would be 2-bromo. 3.3.1 bicyclononane. But what if we didn't do that? What if we tried the number from the other bridgehead? This one over here. Then our bromine would be on the 1, 2, 3, 4 carbon. Okay, so if we numbered from the other bridgehead, we would have the wrong number on our bromine. So we have to number it from the bridgehead closest to the first substituent. Okay, and let's go with D. Oh, that was, I didn't want to. Let's go to B here. So let's try to do our longest chain again. Okay, so since all of these are methyl groups on the end, I just picked one of them. And we'll know the other 2 are going to be substituents. So we're going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, yeah, 6. So we got hexane. We have hexane. All right, so let's see. And we have substituents on, if we numbered this way, 1, 2, 3, 4, 5, 6, we would have 2, 5, and 5 in the red numbering system. If you number it from the other way, 1, 2, 3, 4, 5, 6, we would have 2, 2, 5. Okay, do you see that this substituent, these 2 substituents are going to be on the lowest number if we start numbering from the left side of the molecule? So that's going to give us our numbering system. And since we have 3 of the same groups, 3 methyl groups, we can use the trimethyl. So our answer is going to be 2, 2, 5 dash tri, not with a Y, with an I, trimethyl, and it was 6 carbons hexane. All right, now let's do the last one, D. Okay. And the last one on D, we're going to try to find our longest chain, of course. Oh, look, we've changed functional groups though. We have to put OL at the end of our one, and we have to have that functional group be at the longest, on the longest chain. So we're going to do 1, 2, this would be 3, 4, 5. So that means we have pentanol. Pentanol. Okay, the pent is for the 5 carbons, the ol is for the OH, and the OH has to be on that longest chain. And because we want to start the chain, because that alcohol can start the chain, we want the alcohol at the lowest number. So we're going to say that's 1 pentanol. So that's telling us the alcohol here. The other way to do it is you do pent A and then 1 all. It's just harder to say pent and 1 all. So 1 pentanol is another way to write. Both are acceptable. Okay, so but we have a substituent. We've assigned our number 1 position where the alcohol was. This is our number 2 position. So this is going to be 2 methyl, 1 pentanol. All right, so we followed all our rules correctly. All right, give the IUPAC name for the following one. Oh, I had multiple pages for that. All right. So write the structures for the following bicycloalkanes. Okay, here's the trick. Draw 2 dots on there first. Those are your bridgeheads. And then you look at the number of carbons between each bridgehead and each bridge, and that tells you where to draw all your other lines. So let's do that. So in the first one right here, we have bicyclo. So we're going to draw 2 bridgehead carbons right here. And the first number is 1. So that means we have 1 carbon between those 2 bridgeheads. So I'm going to draw that over here. That's 1 carbon between those 2 bridgeheads. Second number is 1. 1 carbon between those 2 bridgeheads. The last number is 0. 0 carbons between those 2 bridgeheads. Boom, we've done our bicyclobutane. Now let's double check. We have 1, 2, 3, 4 carbons. We have 4 carbons. We have our bicyclobutane. So let's do that same process again. We're going to start with B here and do bicyclopentane, but we don't want to start counting and figure out where everything is. So let's draw 2 bridgehead carbons. Okay, and let's do the first bridge. It has 2 carbons in it. 1, 2. Second bridge has 1 carbon in it. 1. And the third bridge has 0 carbons right there. So now we have bicyclo 2, 1, 0 pentane. Okay, and we have 1, 2, 3, 4, 5 carbons. So we did it right again. All right, cool. So let's do the next one, heptane. Oh no, how do I get 7 carbons there? Well, let's not worry about that just yet. Let's draw our 2 bridgeheads. And we're going to draw 3 carbons between these. So it's 1, 2, 3 bridgehead. And then the other one is going to be 2, 1, 2 bridgehead. And then the 0 here is right in between the 2. So that says that. Okay, now when we number this, we have to number from a bridgehead around the biggest ring first. So this is going to be our 2 position. We could have numbered it here and here. And since we're actually drawing it, we can do it either way. But now that we know where our 2 position is, we can put our chlorine on our system. So we want to do 2 chlorine. So we're going to add our chlorine to this 2 position. CO. Okay, I'm going to do the last one just to see how we can, finish up drawing those bicyclo compounds. Let's start with our bridgehead and our bridgehead, and then we're going to go a 1 and a 2, and then we're going to go a 1 and a 2. And the reason I drew it like that because we have another carbon to get in here, and a 1 and a bridgehead. Okay, so that gives us our 2 bridge, and our 1 bridge. So we've drawn it correctly. So let's count our carbons. 1, 2, 3, 4, 5, 6, 7. We have 7 carbons. That's perfect. Now let's number it. Okay, we have to number from 1. We have to go around one of the larger. Since the left and the right both have the same number, we're going to go 1, 2, 3, 4. Then our next biggest bridge would be 5, 6, and our last one would be 7. Okay, so we go around starting from one bridgehead through the other bridgehead to the next smaller bridge, and then the last carbons are on that smallest bridge. Okay, so it says 7-methyl. So that means I need to put a methyl group right on this 7 carbon. Okay, next. 4 of different cycloalkanes will all yield a methyl cyclopentane when subjected to catalytic hydrogenation. What structures are they? Okay, so in catalytic hydrogenation, what we're looking at is that all of the double bonds are converted to single bonds. So let's look at our product, methyl cyclopentane. So that means we had to have double bonds in this thing somewhere. So let's do one of them where we have the double bond here. And then let's just change the position of that double bond. We're going to put it in the ring next to the methyl group first. Then we're going to put it in the ring slightly further away from the methyl group. And then, let's see, 4 different cycloalkenes yield methylcyclopentane. Let's see, what other isomer can we get out of this? We can put it there, we put it there, we put it here. Oh, we didn't put it here. So that gives us 4 cycloalkenes that when reduced will all give the same product. All the double bonds get reduced. All the double bonds, even though they're in different locations, get reduced to give us the same compound. All right, moving on. The sketch similar curves to those given in figure 4.8, which is right here, for the energy changes around rotation from C2 to C3 bond for dimethylbutane and for tetramethylbutane. Do not need to concern yourself with the actual number of values of the energy. You should just label the maximum and minimum. So first of all, let's try dimethylbutane. So let's see, we have butane and then 2-methyl, 3-methyl. So dimethylbutane. So let's draw the projection first and see where we have it. Okay, so if we have 2 methyl groups, let's start with 1 methyl group up here, CH3, CH3, and our hydrogens here. So we're looking at it from this side. We're going to draw this side first, and then that means this half is the back half. So we're going to draw that back ring and let's put a methyl group down here, methyl group right here, and then the last group, hydrogen here. Okay, so that is our projection. So that's our first place to start with that. Now let's rotate around the 2, 3, and this is the 1, 2, 3, 4. So we're rotating around this bond here and see what's going to happen. So if we start with this structure here, obviously we have these methyl groups all gouged to each other, and these 2 hydrogens are next to each other. So that's going to give us a starting energy. Okay, now let's rotate it. So I'm going to draw it. The next one I'm going to do is I'm going to rotate it this way. And what we're going to end up with is an eclipsed position where 2 methyl groups are on top of each other. Here, 2 methyl groups are on top of each other here, CH3, 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 and then the 2 H's are over here. So what's happened here? We went up in energy or down in energy. Well, we're having the methyl groups butt up against energy. So this one's going to be, we're going to start it, this one as 0 right here. We started at some energy here in this configuration, and we've gone up in energy because we've got into this eclipse position. Now, if we keep rotating the front over, if we keep rotating it, like here, we're going to end up with our next position. I'm going to draw that in blue now. So we have a methyl group CH3 up. We have CH3 over here. We have an H over here now. Now we're only rotating the front. The back stays the same. So our CH3 is here, our CH3 is here, and our H is there. Now we have another where our methyl groups are gouged. But notice that we have both of these have methyl groups with hydrogens with them. So is this going to be higher in energy or lower in energy than our starting position? I think because we have that spacing, just that little bit of spacing, it's going to be lower in energy. So we're going to actually be lower in energy than our starting point here. So on our graph, this next one, we've come up in energy, and our next peak is actually below our starting drawing, our start drawing here. So this is going to be a lower in energy than our start drawing, and definitely lower in energy than our eclipse drawing. So if we continue to spin that around, I am going to draw the next one over here, and I'm going to draw it in green. And so again, we're continuing to spin around. So we're going to come to an eclipse where our back is going to be the same. We have a methyl group here. We have a hydrogen here. We have a methyl group down here. And this methyl group is going to be rotated around. So it's eclipsed with the hydrogen now, CH3. And then this methyl group here is rotated down. It's now down here at CH3. And our hydrogen is going to be up here. Now, how is this different than what we had before? In this red eclipsed, we had two methyl groups butting up against two methyl groups butting up and two hydrogens. Here we have a hydrogen methyl, and a methyl-methyl. Okay, that means that this only has one methyl-methyl interaction. This had two methyl-methyl interactions. So this is going to be higher and lower in energy. It's going to be slightly lower in energy. So what we'll see here on our graph now is that this first one went up in energy. Sorry. On our graph, we're going to start out at that same point where we started here. We went up in energy. We went slightly lower in energy because of our intermediate position here. This is going to be up in energy, but less so than this one because we don't have as many interactions. And so that when we come back down, it's going to give us the same configuration here. It's going to go up in energy again and down. So what we can see from this is that each time you do a projection and you rotate it into an eclipsed position, look at how many groups are eclipsed. The more eclipsed groups, the higher in energy. Then as you rotate it out, the fewer eclipsed or the fewer things in the gauche position, the lower energy it's going to be. So keep rotating that around until you see that energy change. All right. So 43, write the two chair configurations for each of the following and designate which conformation is the more stable. We want to start with cis 1-T-butyl 3-methyl-cyclohexane. All right, so let's use that trick for drawing a cyclohexane first, where we start out with two parallel lines. We're going to draw a bottom and a top here. That gives us our cyclohexane in a chair conformation. And we're going to start with our, why is it deleting? We're going to start with our T-butyl group here, just because we know there it is. And so if that's our T-butyl group, that's our hydrogen here, and this is our one position, because it says 1-terbutyl. So then we have to go to our 3 position, so that's 2 and that's 3. So this is a methyl, okay? But the methyl has to be on the same side of the ring, so we have to actually have it going, let's see, the hydrogen has to go out to be on the top, and the methyl group has to go down to be on the same side of the ring. So see how both of these hydrogens are on the top side of the ring, and both of the R groups are on the bottom side of the ring. Oh, look at that, there's a CH3. All right, so that's the first one. So now we have to flip it and draw the other isomer here. So to flip it, we want to pull this side up and we want to push this side down. So when we draw it, we're going to draw our line the other way with our methyl thing here and now our hydrogen is going to be, it was there. So our hydrogen is going to be here now, and our T-butyl group is going to be there. In this case here, and that's still our 1 position, 2 position, 3 position, our hydrogen is going to be up, and our methyl group is going to be sticking out, CH3. So see how we just moved one up and down and got it into the different configuration. Okay, so these are in equilibrium between each other somewhere. Now, which one's more stable? So when we're looking at stability, look at how big the group is. You want the biggest group on the equatorial position. You want the smallest groups on the axial position. So in that case here, in this one here, the T-butyl group is in the equatorial position, making it the more stable configuration of having it in there, which makes this our more stable configuration. Okay. So let's draw a couple more of those. And, oh, come on. All right, so let's do B, and then I'll let you do C and D yourself. So let's draw our cyclohexane again, using that same trick. Okay, parallel line, point, point. Okay, that looks a little more cherry. We're going to do trans, so the two groups are going to be on opposite sides of each other. I'm going to put the T-butyl group over here just so we can assign it as our number one position, just like we did before. We're going to do our hydrogen here, our T-butyl here. And we have a 3-methyl. So we're going to do 1, 2, 3. So the methyl's here, and it's going to be trans. So that means the methyl group is going to be on the top, and that hydrogen is going to be on the bottom. So our methyl group is on the top. Our T-butyl group is on the bottom. So we have the trans configuration. Okay, so let's flip this over. So we're going to pull this down, push that up, giving us our tilt in the other direction, and this in here. And this produces our thing where we have our T-butyl position is there, and our methyl is now in the axial CH3. So let's see, in this configuration, both of the groups are in their equatorial positions. In the other configuration, both of our groups are in axial positions. So that means that that's going to be the less stable version of this compound. Okay, moving right along to 46. All right, so I have it in 3 parts. So the first part here is specify the missing compounds and or reagents required for the synthesis. We're going to go for trans 5-methyl 2-hexene to 2-methyl hexane. So the reagent we're going to do is we're going to reduce down that. So let's just draw that compound real quick. So we're going to have 2-hexene. So let's do hex. Let's draw our hexene. 1, 2, 3, 4, 5. We want to trans, so we're going to do 2. That's this is 1, 2. That's our hexene, and it is in our trans configuration. And then we are going to put a 5. 1, 2, 3, 4, 5. A methyl, and we're going to reduce that. We're going to react that with something to get to methyl hexane, which is going to be that. So the only thing that's changed here is our double bond has been reduced. We've had hydrogen add across that double bond to give us our problem, which means we're going to do hydrogen with a catalyst, and let's just do palladium. So that's the reagent missing, going from the hexene to the hexane. All right, so the next one right here, we have, again, we're doing a reduction of the double bond. Nothing else changes, so we're probably going to do the reagent for this is going to be hydrogen with platinum, palladium, nickel, something like that. And then our last question here is, the chemical reactions rarely yield products that are initially pure. What evidence by NIR for each of the crude unpurified products from the above reactions would you be able to see in the present? So basically, what's the difference between the starting material and the product? Well, both starting materials would have a bond right there around 1650 for that double bond. And we would have only, and we'd also, on this one right here, we wouldn't have any hydrogens above 3000, but on this compound here, we would have a couple sp2 2 hydrogens above 3,000, everything else would be below 3,000 in the starting material. In the product, the sp2 hydrogens above 3,000 would go away. And in the product here, we have no sp2 hydrogens, so they would all be sp. And in both compounds, your double bond would go away and you would not have any peaks above 1,500 all the way down to around 2,900 because there's no other functional group. Okay, and that is the, and that's the end of chapter 4. Thank you.